Okay. So the next part might be a little tedious. Maybe you can go back to these slides if you ever really need to work with PDB files. So I hope it's going to understand you what the format looks like. But it's nothing I would try to learn by heart or anything. So the PDB file format, as I told you, it originated because people wanted to look at the structures. The latest version of the PDB file format is from 2012. And as I said, the problem we have there is with really large structures, and the new standard for PDB files is, that's got swapped around, so it should be 2014. That is MMSIF. It's supposed to be the new standard, so it's supposed to be the format everybody's using, but there are loads and loads of viewers around that were made for looking at PDB structures, so I'd say the de facto standard is probably still the PDB file format. And also loads of bioinformatics tools that calculate something from PDB are for a large part still based on this old PDB format. So it's still worthwhile to know what is inside that. A PDB file in general consists of some header information and then the coordinates. If you're interested in any bioinformatics calculations, you're usually mainly interested in the coordinates. But if you want to put together a data set which has got certain constraints, then the header is where you look for information like the structure resolution, the method the protein was determined with in general, which protein it refers to, etc. That is all contained in the header. So by definition, a PDB file has a certain defined set of characters that are allowed, and each line is exactly 80 characters wide, and I guess this comes from the old Fortran language where you also had to determine an exact array length and things like that. So you see a lot of old programming paradigms still in the PDB format. Each line starts in column 1 to 6 with a record name, so that tells you what kind of information do you find in that line. Column 7 has to be blank, and then the rest of this can contain information. The records in a PDB file always come in a defined order. That's nice if you write a parser, then you know that if you don't find this kind of record until here, you're not going to find it later. Makes writing parsers easier. I don't know whether anyone of you has ever tried to write a parser for a file like that. So I have, and writing a parser in general is not too difficult. Writing a parser that is not going to fail on any file is really hard. Especially because people also make errors, and especially the old PDB files had errors. So nowadays I think they've done a lot of curation, and a lot of the knowledge I assembled on how to write a good parser that deals with errors is not needed anymore, luckily, but yeah. So some records are mandatory. This is to give you an idea of what kind of records you have. So you have the header. You can have something which tells you that this file is obsolete and has been superseded by a new one. You can have a thing called split, which is the old PDB way of dealing with large structures, which tells you, okay, there's another file you should look in which continues the information you find here. You can have stuff like the source, where it comes from, experimental data, what compound it is. So this is the general setup, so you get an idea of what kind of records you have in there. Then there are different sections. So one is the title section that contains these records. There's a remarks section where you can put in lots of prosa about what you find in there. There's an interesting section which is called primary structure, where you can find the sequence that this PDB chain refers to. That's an information you often want to look at, because then you want to find the actual sequences. There's a section that is concerned with any heteroatoms, so that's not amino acids that are in there. There's some information about the secondary structure too, where the crystallographer or the NMR specialist says, okay, I believe this part of the structure actually is a helix, because there's always a bit of a discussion where exactly does a helix end, where exactly does a helix begin. So they put in that information, what they think is the definition of a helix in the sheet, and some connectivity information. And I think I'm going to skip that because it gets boring. The general record format, just to give you, again, an idea of what you deal with in a PDB file. Here we look at an example of the remarks record, and that can have a substructure, which is that in the beginning, you've got this remarks thing. Then you've got some string that helps you determine that this is like remark 2 and it continues. Then there's the type of the remark that you have. In that case, it's resolution. And then you get the actual value. So if you look for the information resolution, then in your parser, you would say, okay, I want to look for the remark, and then I want to look for resolution, and then I want to look here for the actual data. The most interesting part, as I said, when you want to really look at structured data and interpret that, is that you need to look at the atom and hat atom records. So several groups can be grouped together in this model thing. This is especially important for NMR, as you learned, because there we get different models in the same PDB file. Then one version of the protein structure is grouped together between a model and end model line. Any atom that belongs to a normal amino acid has got the keyword atom in front. And any atom that belongs to something that is not a normal amino acid belongs to hat atom. That is important because for the amino acids, you don't really need to store how the different atoms are connected, because everybody knows what an amino acid looks like. Whereas for the hat atoms, you also need to store the connectivity of the atoms, because you can't really know what you're dealing with. Okay, and then in the end you expect that there should be a ter which ends your chain, and then you know, okay, something new begins here. And again, this is an idea to give you an idea what this atom then atom record then looks like. You got the atom line, then you get a serial number to say, okay, this is the next line. You get the name of the atom. Sometimes you get for one atom different possibilities where it could sit, so you need to see that in the data, and it tells you, okay, this one is for an alternate location. You have the residue name, the chain it belongs to, because in one PDB structure there might be several protein chains bound together, like in hemoglobin, for example, you would get 4 chains together. So it tells you what chain does my atom belong to. The number of your residue in the sequence. And there's a nice specialty, which is that your residue number might have an attached letter, which tells you it's an insertion code. That's a real nice specialty of PDB files, because sometimes when you have homologous structures, for example, in the case of serine proteases, you get that a lot, that people first solve the chymotrypsin, and then they solve the trypsin and the thrombin and whatever, and they said, oh, actually they basically have the same fold. So we're going to try to number the residues in a similar way, but then there are some loops that have a different length. And therefore, for example, in thrombin structures, you often find residue 60, 60A, 60B, 60C, 60D, and then if you want to parse that, that can be really a nuisance. Okay, then in the end, then you get the real coordinates. That's what you're really usually interested in. And you also get some additional information like the occupancy, which tells you, okay, I really see the atom so much there, because in some cases you might not have that much signal for that. This tells you that this coordinate is a bit insecure. You get a temperature factor, which also tells you about how smeared out the electron density was there. And I forgot what the rest is. but these ones are a bit the important points. Actually, the temperature factor, which is supposed to give you an idea of how mobile the atom is often reused to have some other information. If you want to put an annotation on your PDB structure and your viewer doesn't really deal with annotations usually, you sometimes put some other kind of information in the temperature factor field, because then your viewer can color by that kind of value. Okay, so this is an example of what a coordinate section might look like. This is what a sequence in a PDB file looks like. And I'm highlighting that because in a PDB file you have a record which says, okay, this is the sequence this protein was, this structure was determined for. But it might be that in the atom record you don't really see all these residues, because some might not have been resolved because they were mobile and you couldn't see them in the electron density. So when you look for protein structures, it's really the question always, do I want to look for protein structures that contain the right kind of sequence in the sequence record? Or do I want to look for protein structures where I look at the sequence that is implicit from the atom record and I know that, that the residue has actually been resolved? So that's a bit of a caveat when you're dealing with PDB files. And the normal thing that is stored in databases is the sequence from the sequence record. That's why I'm pointing this out. So if you find a structure that should have coordinates for a certain protein sequence, then you still have to look, is it really there in the atom record? Okay, if you want to write if you need a parser for PDB files, there's loads out there. You might be able to reuse one. Writing your own is not too difficult if you don't have it, if it doesn't have to really work on every file you could ever imagine. Here's an example of what using a structure looks, a PDB file parser looks like in Biopol. So you just say, okay, I want to read that file. I then want to get my next structure, and for example, I want to find out the sequence of that thing. Or I want to get a set of all atoms from the structure I've been looking at. And then XYZ would give you, from an atom, it would give you the set of XYZ coordinates. So you see there the parser basically does everything for you. And the same kind of thing also exists in BioPython, and I'm sure there's also the same in BioJava and whatever. So it depends on what kind of language you prefer. Some note about the software architecture. I think it's a good idea to make your software independent of the actual type of coordinate file you're trying to interpret, especially nowadays with the switch from PDB records to MMSIF. It's good if you program in a way that you say, in the end I want to work with coordinates, but I don't really care what kind of parser my coordinates come from. And therefore also in things like BioJava, BioPython, they have programmed it in the way that the interface for reading a PDB file, a normal classic PDB file, and the interface for reading an MMSIF file basically gives you back the same kind of object. So from both of them you get this BioPDB structure object. Okay. So a bit about the MMSIF format. It's standard since 2014, and the general structure of this is a so-called star file, where somebody apparently did some research on how you can, in general, encapsulate data in a self-documenting and generally parsable manner. The advantages of the format is, as I said, for PDB, there's a defined number of, or a defined set of records you can have. There's a defined order the records can be in. The star file explains itself, and you can extend the format. And it's also flexible with respect to order, and there are not so many rules about the exact syntax it has to look, how it has to look like. And because it's self-explaining and self-describing, it's also easier to automate the validation. So you can have a program that looks like, is it really syntactically okay? What is the general syntax? Well, any data has got a name. That is a text string that starts with an underline. So for example, a chemical formula, and that type of data name can only occur once. And then behind that you have a data item that is any text string that doesn't start with an underline. So for example, you might have this, which would be this chemical formula belonging here. So this, you have chemical formula, and then you have the data item, that one. Sometimes you have a number of things at the same time, the same thing a number of times. For example, one structure might be cited in different papers. Then you have a loop, so you define your the kind of data that you're going to get, and then you can put in the actual data item a number of times. So for this citation, we have a number of authors, and one is called Fitzgerald, the other one McKeever, etc. And in order to group this whole thing, you can also precede the collection of data with the data block item, so then it's easier to find something. The thing you want to find from a biology point of view in your MMSIF file would be that you want to find an entity that could be a polymer, a non-polymer, or water. So polymer would be any kind of DNA or protein chain. Non-polymer could be something that is bound, like a chemical compound that is complex. And water, I mean, you know, in PDB structures, of course, you also see your water and you want to know where it's placed. So it's its own kind of entity. So you can have chemical components that are plugs, which build entities together. You have asymmetric unit things. That is, when you have a crystal, the asymmetric unit is the three-dimensional form that builds up the crystal. So that's the form that you repeat again and again to build up your crystal. That is not necessarily the form in which the protein occurs naturally. So for example, in order to build a crystal, it could be that your protein, which is globular, binds together with another one of its instances, maybe oriented like that. And then this two-way complex is then repeated again and again in your protein. But because it's important for crystallographers, the asymmetric unit is also something that is reflected in your PDB structure. Okay, but as I said, that gets boring, and you can refer to that if you really need to look at the structure, at the files, but just to give you an idea. So if you want to find data in MMSIF, for us who are used to PDB, this is really getting used to, because we were used to just looking there at the header and would have any information we expect there, and now it's distributed over different fields. So for example, this line would become, in the struct, you would have the entry ID, which is this one CVN. In title, you would have the name of this structure. Then you would have some keywords, which would say that's a plant seed protein. In the database PDB revision, you would find that it's originally from October 11, etc. Okay, so one important field you might want to look for is the refined thing, where you get the resolution information. And another thing you might want to look for in MMSIF files is the reference to sequence databases, which could be found in those two. Okay, and then from a programmatic point of view, all these different kinds of records refer to each other. So struct_ref refers to the entity ID and to the biological structure, etc. So from a programmatic point of view, there's a lot of logic behind there, but I'll skip that. Finding sequence database in MMSIF is, as I said, you have to look at the struct_ref thing and struct_ref_seq thing. They are two different parts because struct_ref tells you in general that you can find a reference to, for example, UniProt here. struct_ref_seq can limit this reference to a part of your protein structure you're looking at. So it might have an extra field where it says, actually, this part of the UniProt file do I really refer to. Yeah, then you have the polymer definition, where you then see the actual residues that this protein sequence is composed of. So here it tells you it's the entity ID, and then you have the number of the residue and the monomer ID. So this is where you would get the sequence from in an MMSIF file. And you can have that in this format, and you can also have it in a one-letter code. So depending on what you're looking for in an MMSIF file, you would look at either this or that one. For parsing MMSIF files, there are a number of Python modules. There's also BioJava, and it's always a good idea if you want to start writing a parser or using a parser for MMSIF to start at the PDB site, because they provide parsers. So they maintain the parser for their MMSIF because they use it anyway, so it's also, it's always kept up to date because they use it themselves. So I would recommend going to their site and then using one of the parsers they recommend. Yeah. Okay, so if you want to look at PDB structures in 3D, then you can look at the PDB. They refer to current 3D viewers. There are a few very famous tools. One is PyMol, which unfortunately, since it's maintained by Schrödinger, it's not so easy to download anymore. You have to get a license first. But then on the other hand, maybe it's better curated now or better maintained. JMol is pretty well known. JSMol. So JMol is based on Java, but since Java's got loads of problems nowadays with security and a lot of browsers don't support it anymore, people are moving over to JavaScript. And JSMol is the new version for JavaScript. And the person developing JMol, Bob Hansen, is really nice. So if you ever have a problem with JSMol or JMol, and you have really looked at the documentation, then I would encourage you to write to Bob because he's also very responsive. Other tools are Chimera. I don't know that one so well. I think it's more for Windows users. VMD is used a lot in molecular dynamics simulations, and Yasara is also a nice viewer, which is used for teaching a lot. And what I'm showing here are mostly open viewers, which you can just download and don't pay for. So this is to give you an idea of different ways of actually looking at a protein structure. So if you look at all the atoms, you see that can be, you don't see a lot, so it's very hard to get an overview. This kind of representation is called a wireframe representation because it's like if you had loads of wires which are connected. This one is called a spatial representation because it gives you more of an idea of what the protein might look like from the outside. So something interacting with it would not just see empty space, it would basically see something that's filled. But if you want to get an idea of how this is actually folded, this doesn't really tell you much either, and therefore the usual way and the usual first impression style of looking at proteins is where you really highlight the secondary structure. Then what we use a lot in order to display information is that we use color. In this case, we use it for showing the atom types. Here we use it more for making it easier to go through and recognizing the different parts of the protein structure. And another thing we do is use different surfaces. And yeah, in 2010 we wrote a review about how to visualize protein structures. It's a bit outdated now, but I think most of the stuff still exists. So if you want to know more about visualizing protein structures, you could read that review. Yeah, so this is just to illustrate that different ways of looking at structure can help you analyze different aspects. So if you're looking at a ligand, for example, you might want to know, so to a surface, to a ligand, what does the protein around it look like? Then it's helpful to look at the surface, where you maybe color by charge, and then you see, okay, this ligand could interact with a negative charge here, positive charge there, etc. On the other hand, you might want to look at, what does my ligand look like to the protein? But if you do those two together, then you don't see anything anymore. Therefore, it's also important, if you really want to work with a protein structure, you often need to switch between many different ways of visualization. And if you want to publish a paper where you explain what your protein looks like and what it does, then you have to fiddle around with that a lot to find the view that really tells your readers what you try to convey. And it might, so this picture is supposed to show you that it might also help to not really look in 3D at all, but to look in 2D, because then it's easier to highlight ways of interacting. Okay, so I'm going to talk a bit about Aquaria now, which is the tool I was involved in developing. I'm going to show you what it is, and then talk a bit about the history of how we developed that. Okay, so what's the main idea behind Aquaria? Well, the main idea is that if you look at PDB, and here you see an excerpt of loads of interesting structures you have in PDB, then, oh, that's still the out number. The number of structures we have in there, or is it? I don't know. In 2015, I think it was 110,000. And if you look at how many unique chains that was like 70,000 or 71,000. So that's a huge number of structures you could be looking at. If you look at what is the way that the PDB usually presents a structure, you see that there's loads of text information and the structure is not so prominent on there. And we thought, well, there must be a better way, if you're interested in a protein sequence, to really look at the structure, better first entry point. Of course, to a crystallographer, all that is very interesting, and also seeing his citation there is interesting. But if you're a user, then you're more interested in that part. And I also told you that there's a lot of growth in the PDB, but actually the growth in the number of sequences is even higher. So if you look at what number of sequences we have in Tremble, which is the database where you basically collect all the protein sequences from any source, not curated, and then look at how much of that has actually been curated, then you see only a very small percentage of that has been curated. And the sequences we're really usually interested in are those from SwissProt, which are the curated sequences. That's the one we are focusing on. Okay, but from these, if you look at how many of these do actually refer to a structure that had been determined experimentally, you see again there's only a very small percentage that has been resolved experimentally. But you've probably also learned in bioinformatics, meanwhile, that similar proteins often adopt a similar structure. So we said, okay, we might not be able to show you a protein structure for your sequence, but we can show you something that's probably going to be very similar, so you can at least map your protein sequence to this other known structure, and then infer some properties of your structure from this mapping. So we don't really build a model. We don't go through the whole process of really exchanging the side chains and everything. We just take your sequence and map it to the other structure. But then you can see out, okay, which parts of the sequence are probably on the surface, which ones probably interact with the ligand. This is something you can completely see from just the mapping. So that's the idea behind that. But actually doing that, making all this calculation, looking at those big amounts of data is too much for most biologists. So what most biologists do with respect to the problem of how do I get a structure is just to stick their head in the sand. And we said, no, this can't be it. We want to help them. And that's why we said, okay, we're going to start completely differently. We're going to start with your protein sequence you're interested in. You don't have to know anything about PDB, anything about model building. You start with your protein sequence you're interested in. That's this sequence. And then we're going to show you which parts of the sequence can be mapped to any protein structure. And we use coloring to highlight in this schematic representation which parts of the sequence have got any kind of secondary structure. And we also use coloring to highlight which residues are really identical, and that's the one you see in bright full colors, and which parts of the sequence are different between you and the protein structure we're mapping onto. So through that you can get a very quick impression, is my protein really going to be similar to that structure or not? And yeah, so we also use the same kind of coloring scheme in the structure we then show. So this is going to tell you, okay, probably my protein is going to be structured very similar, but I have to be careful in the core here, something might be different. Okay, so for any protein you're looking for, this is the view you get when you look at an entry in Aquaria, which tells you, okay, in this region, and we cluster together any proteins that's mapped to the same region, you've got 87 structures that map there. Or you also have further down a cluster which consists of 6 structures that map to this part of the sequence, but they match at a different level, at a different highest level of sequence identity. So depending on what your question is, you can then, as a user, decide that I want to look at this shorter set of structures because I'm interested in some atomic details and I don't really care about the rest, or you want to look at the longer set of structures because I want to know something about the whole protein and I'm not so much interested in the atomic detail. So that's the concept behind Aquaria. This is what the Aquaria homepage looks like. We try to make it easy to search for structure, for proteins, because the biologist coming in might not know the identifier for his protein or anything. So we've got the synonyms search. I hope by the time you are going to try this, our synonyms indexing is going to be finished again because our production server currently has a problem. Because there are so many proteins now that the number of synonyms we have has become so big that our indexing process is now for the first time taking too long, and so it's a bit slowed down at the moment. But you can still find stuff at the moment by the PDB identifier. But in general, the idea is you go in with any name for the protein and it's going to suggest, for example, P53. By default, we limit the search to Homo sapiens proteins because otherwise you're going to get too much choice. But if you know you're looking for a different organism, you can tell this thing here, I'm looking for, I don't know, the cow or whatever, and then you're going to get the choice from cow. And then by default, it loads your sequence and the best matching structure, where the definition of the best matching structure is the structure with the most residues identical to your protein sequence you were looking for, and with the best resolution. And again, we're going for resolution because it's the safe way to go. People are not used to dealing with NMR. Okay, so then you can scroll down further in the list. And here on the left-hand side, we show you the sequence identity of the best hit in that cluster. So you can go down the list, and you can click on this number, and it's going to show you what structures are underneath that. So for example, there are two structures where TP53 has been co-crystallized with DNA, or there are 5 where you have a dimer of TP53 and a dimer of DNA, etc. So it helps you get down to more detail if there's something specific you're interested in. And if you want to see the P53 complex with, for example, here's another TP53, then you can say, okay, I want to look at that structure because this can help me analyze the interface. And you can even click on that number again, and then it's going to show you more information about the specifics of that structure. Okay, you can, if you want to, so this is a Java viewer, which we've built. Specifically for displaying in a way that's easy to understand. The problem is, again, we're dealing with Java, and we're currently trying to get someone to program us a nice JavaScript viewer. So I hope within this year or next year we're going to be able to really switch to the new JavaScript viewer. At the moment you still need Java here. We also have a basic JavaScript viewer, but it's not as nice as that one. Okay, for the Java viewer, we've got a card of how to use that. So this is just for reference. And now I was also supposed to tell you a bit about how we built this whole thing. So we do some time travel back to 2003. So that was about 3 years after my PhD. I joined Lion Bioscience, which Lothar mentioned was at the time a big star on the new market. Bioinformatics company and growing fast. Unfortunately, we grew too fast, and so we didn't really make money, but we burned money. And in 2005, more or less, the people who had been giving us money said, well, we're fed up. We want to have you make revenues. And so they retracted money, and our management left, and then Lion Bioscience folded us again. So much for my big plan of studying quickly, making a PhD quickly, entering industry, and then having kids because they know me. Because in 2005 my first kid arrived and Lion closed. So I'm a bit now for just do what you think is best for you and don't make plans. Okay, so what was the story behind SRS 3D and Aquaria at that time? Well, one of the big assets of Lion was the so-called sequence retrieval system. Because at the time, most biological databases were not in any kind of MySQL or whatever, but most databases were just flat files. And everybody who did experiments and collected interesting data defined his own flat file format for his type of information. Now, if you wanted to look for information from one database and another database and relate that to a third database, it was an extremely tedious process. And there was a person named Ture Etzold at EMBL who has written this service, which was basically a way of indexing the biological flat file data and making cross queries across the whole thing. And together with Lion Bioscience, SRS has more or less died. It's still being maintained a bit as far as I know, but there is also still an installation of SRS at the DKFZ in Heidelberg. And if you ever have the problem of really having to search across different databases, different of those flat file databases, it might still be a good idea to have a look at that. Okay, in our case, what we wanted to do is to have also 3D information in there. So sequence information, annotations, etc. was also already in there, but we wanted to put in structure information. And, oh yeah, this is what SRS looks like. So you've got loads of databases you can search from, and then define which fields and which database you want to search in. And this is a bit of the universe of databases that was connected by SRS. So each of those lines is a connection where you can say, okay, I can hop from EMBL to, I don't know, SwissBroad, and from SwissBroad I can hop to Enzyme, etc. Okay, so since this was all based on flat files, and indexing of flat files and having links between flat files. We also had to put in this structure data and make links between the sequence files and the PDB flat files. So we had to, and also the alignment information between a PDB file and a sequence file, we also had to put this in some kind of format that could be indexed in that system. And we also had to generate all the alignments. Like in a query nowadays, we have to generate alignments. We had to generate information alignments at that time. At that time, we used the HSSP, which had been developed by Burkhard Rost, who was a good friend of Sean, my boss in Lion Bioscience. But he's also really done a good job. Oh no, HSSP was actually developed by, again, someone else, but he was using information from Burkhard. Anyway, so this was a really good way of aligning sequences to structures because it was kind of the first profile alignment method. Nowadays, you're used to having SciBlast, etc., but at that time, that didn't exist yet. So that was a good way of really having high-quality alignments because you use profiles from the structure, profiles from the sequence, and where it was able to align that together. And so from the set of, and unfortunately it was too slow to really process all of Swissprot, therefore we had to have a first filter, so we used the Swissprot database, or at that point Swissprot and Trumbull did a blast against PDB, and then afterwards we could use HSSP to get alignments. Yeah, since the time is running out, I will skip that. I'm sure if you go to one of Burkhard's lectures, he's going to show you that part.
You have until 11:45.
1:45. Okay, I thought it was only 1:30. Well, anyway. Okay, so for indexing, we then had the PDB, where we took out the sequences which we indexed, and we had the we had to map the sequence. I showed you there was the sequence record in PDB, and we had to map that to the actual atom record because we had to know, does this atom actually really exist in 3D? So for every PDB structure, we had two records. One which said, okay, this is the sequence it claims to have, and this is how it maps to the actual atoms. We had the Swissprot database. From that we got the HSSP database where we would have the matching. How does the sequence match to a PDB structure? And a HSSP file was a bit hard to parse, therefore we took it apart into something that would list for every sequence all the structures that match, for every structure all the sequences that match, and the actual alignments. But this was basically because that fitted the data or the environment we had to work in there. Okay, so then we could link from Swissprot, we could link to loads of other databases, and here we could link between the structures and the data and the sequences. And then we could have a viewer which would, for example, load in annotations from Interpro, it would load the sequence you're interested in from Swissprot, and it would load the alignment information from our PSSH and HSSP align database, and it would load the actual structure data from the PDB database. Okay, let's skip over that. So this is what SRF3D then looked like. So you would search in here, you would get a result set. If you clicked on that, you would get the set of structures aligning to your sequence. And for each of those things, we had to always write a parser for the data, a way that defined what this view looks like, and also something that loads the data from the parser and gives it to the view. So that was the kind of architecture we were working in. And then this was the site, SRF3D. Actually, the site still exists, but it redirects you to Aquaria now. Something a bit about the database that we now have behind Aquaria. as I told you, if you look at switchplot, you can find structures in there that really refer to, or sequences in there that really refer to a structure for about 4% of the sequences. But we want to expand from there. Therefore, we need those alignments. In 91, Schneider and a few others developed this HSP method, and it was called homology-derived structure of proteins. That's where the abbreviation comes from. Then in 2003, when we developed the SRS3D thing, and we wanted to list, so this one lists sequences similar to the structure for one reference structure. And because we wanted to have all this indexing, etc., we had to turn that around. So for any sequence, we could list all the structures, and then we thought, okay, what name do we give this thing? And we just turned the name around too. That's why it's called PSSH. And then for that abbreviation, we invented a name. In 2000, so as I told you, in 2005, Lion Bioscience died, and so we all dispersed in various parts of academia and non-academia, whatever, but especially Sean and myself said, this was such a great project, and we really thought it was valuable, we don't want this to die. And in 2009 or in 10, we at last both had found a new place to work in again. So Sean had gone back to Australia, and I had started at Rostlab. And that's when we really started resurrecting this whole thing in the public domain. And at that time, we re-evaluated how are we doing our alignments. And you saw the growth in databases, and it was just not feasible anymore to use this old Maxim HSSP program. And we said, okay, we have to come up with something new. And then we completely re-evaluated this whole process, and that's why we called the new database that has arisen from that now PSSH2, because it's like 2.0 version of that. We went in and looked for what other methods are in there. Just using SciPlast didn't seem like an extremely reliable method. SciPlast is good, but we felt there must be something better, so we looked at InCAST, which is the competition for doing protein structure modeling. We looked at who comes out good. And actually HHBlitz, the method that was also developed here in Munich, always came out pretty well in those modeling tests. Plus also it was of course an advantage that Johannes Söding was here and we could talk to him in person and ask him for advice, so that was really nice. Yeah, in 2010 they were still pretty much on top, and the other advantage of HHBlitz with respect to all the other things is that it's extremely fast. That's also, by the way, why it's called HHBlitz. It's, although there isn't a Z here, it kind of suggests our German Blitz. Okay. So what's the background behind HHBlitz? I don't know whether you've done that in any of your bioinformatics yet, profile alignment things. So the idea behind HHBlitz is that you produce a profile of your query sequence and also a profile of and you have a database of profiles you're looking for. So you don't just look sequence by sequence and try to align, but you know which parts of your sequence are actually important for determining what family your protein really belongs to. And profile search methods can be extremely slow, and the cool thing about the HHBlitz group is that they found a way to encode a profile in such a way that you can do kind of a quick alignment of a more or less one-dimensional representation of that profile, and then you go in back and you do a precise thing. But you have a really good pre-filter for looking at what profiles you really look at. So that's the main message of that thing. So what they do is they go through the whole UniProt and they produce profiles for UniProt. Of course, because UniProt is huge, they have to cluster a bit for redundancy, etc. Okay, so in the, and they use hidden Markov models, which would be too long to explain now. So in UniProt 20, you've got about 4.8 million clusters where sequences are clustered together if they have more than 20% sequence identity, and also almost the full length of their sequence is covered, and they have 80% coverage. Okay, so each cluster has a multiple sequence alignment, each cluster has a profile, and each cluster also has this 1D representation of the profile. So that's the information that is put together in this UniProt 20 thing. Okay, we did a validation where we looked at structures which were defined in a database to be similar. So this is what was in this top-match COPS database. They cluster together structures that are structurally similar, and then we took a sequence representative from that, went through the whole process of building a profile for our sequence, scanning it against the profile of PDB sequences, and see, can we find it again? And then if we found a structure, we looked at, is it defined to be similar according to this database? And then you have two measures, which is the false positive rate and the true positive rate. So we want to find as many structures as we can without finding those that are wrong. And we did that experiment for Cyblast and for HHBlitz. And as you can see, at any given false positive rate, HHBlitz finds more of the true positives. That's how we validated that HHBlitz is really going to give us a better performance. And also, on top of that, HHBlitz is even faster. So that's why we decided, okay, HHBlitz is a really good way to go with. And then we still had to define what are we actually going to show our users. Because we want to give the users the chance to find a protein structure as much as possible, but we don't want to show them stuff that we think might probably be wrong. And therefore we did this, we looked at the curve of precision against recall, and we looked at, okay, at what point are we going to define our cutoff? And if you look here, the precision, it goes down here, but there's a certain point where the Steigung in English, where the steepness of the curve actually becomes a lot more. So we kind of cut here with 10 to minus 10 expectation value, and there you have a pretty high recall, and your precision is still above 70%. So, I mean, you can debate what is a good way to go, but since we're also coloring our structures and really making it obvious if your sequence identity is low, we think that it's still a valid way to go. So you might get something that is wrong, but you have a high probability of getting something that is right, and you still get it. And note, I mean, if you're used to expectation values, I mean, very often people cut at 10 to the minus 3. In the stuff that we saw, that we would say 10 to the minus 3 is pretty broad. So you might already get quite a lot of false positives there at 10 to the minus 3. Okay, so our workflow is from UniProt, we get this UniProt 20, which is provided by the HHBlitz people. We take the PDB, every sequence from PDB, we scan it against UniProt to make a profile HMM of the PDB. Every sequence from SwissProt we scan against UniProt to make a specific profile for that sequence. And then we scan that profile from SwissProt against the database of profiles from PDB, and that is how we determine our database of PSSH. So we can go from 4% coverage for SwissProt just by references to 88%, where for a certain protein that you're looking for, we can at least give you information about some part of the sequence. So it doesn't mean that the whole sequence is going to have structure, but it means that for 88% of the sequences in SwissProt, we can show you at least parts mapped onto a structure. And this thing, so our PSSH database at the moment has around 126 million alignments. And if you look at, on average, how many alignments you get per protein, that's about 160. So in some cases, it's going to be a sequence, a structure that is really similar. In other cases, it's just going to be like 20% sequence identity. But we give you all that choice. Okay, and then we also had reinvented the whole technical setup. I showed you before in SRS3D we had all these different pages, and now in Aquaria we decided, okay, we can combine this in one page, because this was due to the adhering to the, I mean, we had to fit the framework we were working in, but then we thought of, okay, what does a user really need to see? And we decided that what they need to see is more something like that. And on the left-hand side, you see information about the sequence you were looking for. On the right-hand side, you see information about the protein structure you're currently looking at. And then here in the main thing, you see the protein. You can actually visualize the protein structure. Okay. We didn't have to work with SRS anymore with this flat file based indexing, but we now put it into a relational database. So our protein sequence, the main thing we're using for identifying protein sequences, just as a note, is the hash of the protein sequence. Because, you know, a sequence entry in UniProt can change its name, and the exactly same sequence could exist in a number of organisms, especially in case of those bacteria. You might have a different entry again for each different organism that the sequence is found in. And we're saying, you know, for the alignment, we don't really care which organism that thing comes from. So the really identifying thing for a sequence for us is just the MD5 hash of the amino acid sequence. That's what we always refer to when we want to look for alignment. But then we can refer a protein sequence entry can have the same hash in different organisms. A protein sequence entry can have synonyms. It can occur in different organisms. The organisms can have synonyms. So this is all a set of tables that is related, and we thought a lot about how do we best represent the data. For a PDB, again, we have a PDB entry which collects all the information that will be in the header and the old PDB files, or that will be in the general information in an MMSIF. Then we go to an individual protein chain, which refers to all the amino acids, etc. And again, that one has an MD5 hash of the sequence. We also had to think a bit about saving space, because the normal alignment you see, you know, when you look at a cluster or whatever alignment, then this is very redundant. Because in principle, when we want to know that this structure aligns to that sequence, we know the sequence we're thinking of, and we know the sequence of the structure we're thinking of. So we don't really need to store all the amino acids again. And therefore we said, well, the best way of having this in an easy way to store is that we always match the part of sequence. So we say residue 1 to 22 matches to residue 16 to 37 of that PDB structure. Okay, I think I've covered that. Some cool features of Aquaria, what I think makes it pretty special is, as I said, we don't only show information from UniProt and PDB, but like in the old SRS concept, we also tap into all the other information there is about a protein sequence. Therefore, apart from the matching structures section, we have this features tab. So you can click on that, and in this example, this, for example, is a membrane protein. And one of the first questions you might have when you look at a membrane protein is to know, well, what is actually inside and what is outside. And so usually you would have to go to some other database, look that up. But here we load the information automatically from UniProt, and you can just highlight, click on this feature annotation lane, and it's going to color your structure. And it tells you that the yellow is the cytoplasmic region and the blue is the extracellular region. So just by one click you can get an orientation in your structure. And working in ROSLab, where we're interested in, okay, what are the effects of mutations, we also built an interface where you can say, okay, the features that we show here can't only come from UniProt, but they can also come from something external where you can just load that information. And there we have the predicted effect of mutations, and we can say, okay, any mutation in these helices is predicted to be bad for the function. Any mutation in those things outside is predicted to be neutral and not have an effect. This is just an example to show how you can use a Aquaria to visualize stuff. Okay, so that's the team behind Aquaria. And yeah, that's the end of my lecture. If you have any questions.